Hello. Today we're going to talk about the nucleus of the atom, nuclear reactions, radiation, and applications of the nucleus. First, let's quickly review things that we already know. In the standard model discussion, we discussed that there are leptons and quarks, also known as fermions, and that generation 1 fermions, electrons, and up and down quarks, actually make up the majority of the matter that we interact with on a daily basis. We also discussed the 4 fundamental forces of nature and included the 4 particles that act as force carriers, or the 4 types of particles that act as force carriers between different types of particles. All the physics that we know has led us to the following. The nucleus is made up of a dense and positive nucleus, or the atom is made up of a dense and positive nucleus. That nucleus consists of not only protons, but also neutrons. This is where the majority of the mass in the atom resides, because we know from all the physics that has occurred in the last century and a half that neutrons and protons are relatively massive. What do I mean by relatively? An individual neutron and an individual proton do not weigh a whole lot in the grand scheme of my life. However, we also know that a proton and a neutron are each about 2,000 times more massive than an electron. So they are relatively massive when we are talking on subatomic scales, but they are not too terribly massive if we are talking about macroscopic scales. So we also know that electrons surround the nucleus of the atom in discrete energy shells that we often call orbitals. We know that electrons are negative, we know that protons are positive, we know that neutrons are neutral. So, how does the nucleus work then? If the nucleus contains protons and neutrons, then what holds it together? It turns out that the strong nuclear force is what holds the nucleus together. As stated in previous presentations, the strong nuclear force is the strongest of the 4 fundamental forces. However, it acts over incredibly tiny distances. And so in the nucleus, while there would be a natural electromagnetic repulsion between all of these protons, the strong nuclear force pulls it all back. A good way to think of what the strong nuclear force is doing is it's kind of like when you hang out with your significant other's best friend. Even though you can't stand them, you're naturally repulsed by them, but you hang out with them because there's something stronger, like the affection for your significant other, bringing you together. But when the opportunity arises and you're not with your significant other, you don't then hang out with their best friend because you are, in fact, repulsed by them. This is what happens in the nucleus. The protons are naturally repulsed by one another, but they stay together because the strong nuclear force gives them a reason to stay together. But with a little bit of deformation, the strong nuclear force disappears. And now what was binding those protons together is no longer there, and their natural repulsion drives them apart. So what happens if a particle comes into the nucleus and hits it? If the nucleus begins to deform a little bit, the strong nuclear force loses its grip. It can't reach anymore and keep all those protons and neutrons together. As the nucleus begins to deform, those 2 parts of the nucleus will begin to pull apart into separate nuclei, new separate nuclei. So the nucleus of the atom will actually begin to tear apart if we can deform the nucleus just a little bit. So that's all great to know. But one of the things that's going to come up is nuclear equations. So we need to take a moment to talk about notation. Something that's going to come up a lot is this. This is the notation for the nucleus of an atom. That A is for mass number. The Z is for the atomic number or the number of protons, which I can't fit there. So the Z is for the number of protons, and the X is actually the chemical symbol for the nucleus. Okay, so the X is something you'd find on the periodic table The A is for the atomic mass number, and the Z is for the number of protons. Number of protons you might also know as the atomic number of an element. I want to be very specific that this top number, the letter A, or symbolized by the letter A, is a mass number, otherwise known as the total number of protons and neutrons in the nucleus. Okay, it is not a number in grams or kilograms or anything like that. It is not a molar mass. It will be a whole number of particles, the number of protons and the number of neutrons. Things worth noting are that on the periodic table, the atomic mass that you see there, that usually goes out to 3 or 4 decimal places, is the average atomic mass of a nucleus for that element. And it is usually the result of combining a weighted average of isotopes and regular atoms with how prevalent they are in the environment. Also, if we change some of these numbers around, we can actually make adjustments to the atom. An ion is an atom with too many or too few electrons. It is a charged atom. The only way to charge an atom is to adjust the number of electrons as they float on the outside, and they're easy to add or remove. An isotope is an atom with too many or too few neutrons, and these occur sometimes in nature. We're all familiar with carbon-14, right? A certain percentage of all the carbon in our bodies is in fact a radioactive isotope known as carbon-14. If we change the number of protons in the nucleus, what we've actually done is change the nucleus entirely. We've switched to a different element. Changing a proton can take you from gold to platinum, but radioactive platinum, so it's not really highly recommended. Radioactive platinum, what do I mean by that? Well, it turns out that there are 3 types of radiation that can be emitted from the nucleus of the atom. What determines if a nucleus is going to be radioactive? If you look at this chart, it's actually the ratio of neutrons to protons in the atomic nucleus. It turns out that there is a band of stability in which nuclei tend to be reasonably stable. It's typically between about a 1-to-1 neutron to proton ratio and a 1.5 neutron to proton ratio. Not every nucleus follows this rule, but if we find atoms outside of this band of stability, it is almost guaranteed that they will be radioactive emitters. What are the 3 types of radiation emitted from the nucleus? The first type is known as alpha radiation. Alpha radiation is basically a high-energy helium nucleus that is emitted from the nucleus of another atom. Okay, so it's not your regular helium nucleus. It doesn't have any electrons attached to it, though it will quickly neutralize because it will attract 2 electrons to it pretty easily. Alpha radiation, it comes out at a high energy because it is in fact being emitted from the nucleus. And so if you have a positive nucleus and then a little positive alpha particle that's made up of 2 protons and 2 neutrons, it's going to rapidly repel away from the nucleus of the original atom. And so again, it is a high energy helium nucleus that is emitted from the nucleus of an atom. Beta radiation is a high energy electron emitted from the nucleus of an atom. An electron emitted from the nucleus of an atom. How is that even possible? I'm pretty sure I clearly stated that there are only protons and neutrons located in the nucleus of the atom. Well, if you look back at the standard model talk, there are in fact nuclear reactions that occur where a neutron will decay into a proton, and in the process, it will emit an electron. That electron is a high energy electron known as a beta particle. It will also emit with it an electron antineutrino. The other type of decay that could cause beta radiation, it actually causes beta positron radiation, is when a proton decays into a neutron and then it emits a beta positron and an electron neutrino. This electron, like any other electron, is negative. A positron would be positive. And again, it moves rapidly from the nucleus of the atom because it has been ejected out with force. The last form of radiation is known as gamma radiation. If you recall, when we talked about Bohr's atomic spectra, we discussed that the atom consists of a dense positive nucleus with protons and neutrons. We've heard this before, even already today, surrounded by discrete energy orbitals on which electrons reside. And we also discussed that when an electron jumps up an energy level, When it jumps back down, it will actually give off energy in the form of light. It turns out that the same thing is happening inside the nucleus. In the nucleus, protons are actually oriented in energy levels. And when protons move up energy levels and back down, they also give off light. But that light is at a significantly higher energy. So it is in frequencies in the gamma range instead of down in the visible light spectrum, like what we see when electrons shift. So now let's take a look at these three forms of nuclear radiation. Alpha particles, with 2 protons and 2 neutrons making them up, are actually 8,000 times more massive than a beta particle. With 8,000 times the mass of the next radioactive particle, this actually makes them the slowest of the radioactive particles. And with a charge of +2, it's also neutralized very easily, quickly picking up stray electrons from its environment. Alpha radiation tends to occur with the heavier elements and as the neutron-proton ratio increases on the periodic table. Heavier elements will emit heavier radiation quite regularly. Keep in mind, alpha radiation is heavy ionizing radiation, so it will do damage to your cells. A beta particle or a beta positron is simply the mass of an electron. It can move very quickly. However, it is also easily attracted to positive ions and will neutralize relatively easily. Beta radiation and beta positron radiation tend to occur when the neutron-proton ratio is a little bit lower, but still outside the band of stability. This is because we are not making a mass shift in the nucleus, but rather changing the number of protons that are in the nucleus and then ejecting that high energy electron. Also, this is ionizing radiation as well, so keep that in mind. Gamma decay, however, actually doesn't diminish the nucleus at all. When we eject an alpha particle, we lose 2 protons. We shift on the periodic table. When we emit a beta particle, we shift 1 proton. We move up on the periodic table, right? But gamma radiation doesn't emit or doesn't change the nucleus of the atom at all. So it just continues going. It has no charge, so it's not attracted to anything. And it moves at the speed of light because it has no mass at all. Gamma radiation can occur with any radioactive element in the periodic table. Gamma radiation is non-ionizing radiation, yet it is a photon at high enough in energy that it can also do damage to cells. Because of the differences in these particles, it's in fact easier to stop some than others. Alpha radiation, with its ease in neutralizing and its slow speed, can actually be stopped simply by sheets of paper. Beta particles, though, with their higher speed, actually take a little bit more material to stop them. Thin metals like foils or thick pieces of wood or plastic are what's required to stop a beta particle. Gamma radiation can penetrate most things, and in fact, or maybe not most things, gamma radiation is more penetrative and actually requires 10 centimeters of lead to stop it. Now let's think about this. When we go for X-rays, they're exposing us to high energy photons now. Why don't they put us in 10 centimeters of lead? They put us in a vest, but they don't put us in 10 centimeters of lead. Why is that? X-rays aren't as high energy, so they're actually able to protect you with a thinner layer of lead. When you go for an X-ray, they're able to protect the body parts that are not being exposed to, that you don't want exposed to radiation. Because of the different charges that these particles have, each of them is moved in a different direction when affected by a magnetic field. Beta particles will shoot in an opposite direction from alpha particles, and gamma particles will go undeterred, undeflected through a magnetic field. How do you identify if radiation is present in your environment? Well, there's more than one way to do it, but the best way to do it is using a device called a Geiger counter. Once upon a time, people weren't as scared of radiation. These days, you start to mention radiation and people start to freak out. Oh my gosh, radiation, you're gonna die, but you're radioactive. Bananas are radioactive. If you have a granite countertop, that's radioactive. So once upon a time though, they used to manufacture plates with radioactive glaze in them to make them red.
Hi, this is a brief video on vintage radioactive Fiestaware, frequently referred to as radioactive red. Fiestaware was first introduced in 1936 and is in production today. Fiestaware offers many colors and has been popular throughout the years. Here we have a vintage radioactive red plate purchased on eBay.
So this is where he pulls out a Geiger counter. He's going to show you background radiation, and then he's also going to show you how the Geiger counter reacts to the plate, and then he's going to go ahead and adjust the scale on the Geiger counter by powers of 10 every time until he can get an accurate measure of the number of radioactive particles per minute being emitted by this plate.
And is one of the more sensitive of the civil defense era Geiger counters. Actually, I believe it is the most sensitive. What we've done is replace the standard probe with a pancake probe. And this probe has the advantage of being able to measure alpha particles in addition to gamma and beta. The original probe with the Geiger counter would only measure gamma and beta. What we're going to do is turn the Geiger counter on, and we're going to get a background count. The meter scale that you're looking at on 1X is 0 to 300 counts per minute. It appears from the reading that the background radiation is around 60 counts per minute, 60, 70 in that area. We're going to introduce the plate, and I'm going to hold the probe a few feet above the plate, and as you can see, the needle is already pinned on 300 counts per minute. We're going to change to the 10x scale, which would now give us a full scale of 3,000 counts per minute. And as you can see, as I come in with the probe, the scale's pegged again. We're going to go to times 100. This now gives us a full scale of 30,000 counts per minute.
Wow, that's all I got to say. Wow. Enjoy your dinner, kids.
So as you can see, we're at about 27,500 counts per minute. And if I move the probe just away from the plate, it stops and goes back close to ambient.
So, what in the world did we just witness there? That was a plate that was made with a radioactive glaze. And what we observed was a very sensitive Geiger counter that has the ability to adjust scale. And as he continued to adjust the scale, we could see that that plate was giving off a very different level of radiation from background. But it's worth noting that there is always background radiation present. The other thing that I would like for you to note with that video is that when the Geiger counter was moved just a foot or so away from the plate, the number of counts per minute dropped dramatically. And this is important when we think about things like your cell phones. Your cell phones, about 10, 15 years ago, were changed into the category of possibly carcinogenic. What does that mean when they say they moved phones to being in the category of possibly carcinogenic? Well, it turns out that there is a limit put on the specific absorption rating of your cell phones. You can take your cell phone model and Google it and look up the specific absorption rating for your phone. This limit was put in place because all radio frequencies give off thermal energy and the body absorbs thermal energy. Basically what happened is the World Health Organization couldn't say with surety how the increased exposure to cell phones and that thermal radiation will actually affect the body. There was some connection to gliomas and I believe a type of neuroma, but regarding other types of cancers, the results were inconclusive. Ultimately, they got moved into the category of possibly carcinogenic because the World Health Organization had concerns about the amount of exposure that young children who still have soft skulls have to this radiation. But it's worth noting that, again, those radiation levels and those thermal energy levels, the heat that's given off, they drop dramatically simply by moving a foot off axis or a foot away. So it's worth holding your cell phone out about a foot from your body and putting it on speakerphone until the World Health Organization can tell us more. What exactly was the Geiger counter picking up? It was picking up individual radioactive particles. How does a nucleus give off radioactive particles? We've already discussed how the nucleus becomes unstable when it becomes deformed just a little bit. Things that contribute to the natural deformation of the nucleus are when its neutron-proton ratio becomes too high and particles start shifting position. It will start to leak off particles. Whether or not an individual nuclei is going to give off a radioactive particle is actually a completely random event. But it turns out that we can predict with reasonable certainty when half of the particles in a radioactive substance are going to decay. So while we can't pinpoint when an individual nucleus will decay, we can look at a sample of, say, 100 or 1,000 and know the time that it would take for 50 or 500 of those nuclei to turn into different nuclei. That time that it takes for half of a sample of radioactive nuclei to turn into other nuclei or to decay is known as half-life. When you look up the definition of half-life, you will often find something to the effect of the time it takes for half of a radioactive substance to disappear. I take strenuous issue with this definition. You are not actually watching radioactive material disappear. If it's uranium and it's an alpha particle emission, you'll see half the uranium nuclei turn into thorium nuclei. If it's beta radiation, you'll see half of the uranium nuclei turn into neptunium nuclei. But the material is not just simply disappearing. The other important thing with this is that it's the time it takes for half. We've already watched the modeling presentations from last week, and we know that half-life does not mean half, and then the other half is gone. It means half, and then half, and then half, and then half, and then half, and so on until eventually we can't get rid of any more here, until we eventually get down to one nucleus, and we're waiting for that one single itty-bitty nucleus to decay. But again, the other nuclei have not disappeared. They're still here. They're just unusable, or maybe usable for other things. We use half-life frequently to determine the age of fossils and things of the like. We can look at the decay of carbon-14 and that decay cycle, and look at the amount of carbon versus the amount of nitrogen in a fossil to actually determine the time range in which that animal died. It will not tell us when it was born. It will not tell us the animal's age, but it will tell us when it died. Another thing worth talking about is mass defect. It turns out that if you were to take a look at the nucleus of, let's say, a carbon atom, 6 protons and 6 neutrons, if you added up the mass of 6 individual protons and 6 individual neutrons, you would actually get more mass than if you figured out the mass of a carbon nucleus by itself. Where does this difference in mass go? This difference in mass is called the mass defect. One of the things that Einstein's famous equation, E equals mc squared, gives us is that that mass defect is actually mass that is completely converted into binding energy, the energy that binds the nucleus together. So if you consider that if you exercise really hard and do put a lot of energy and a lot of effort forth, you might ultimately lose weight. Consider that to be what's going on inside the nucleus of an atom. In order for all those protons and neutrons to want to stay together, they have to put a lot of energy into that, and the result is that they lose weight. They lose mass. It gets converted into energy to bind it together. It turns out that one atomic mass unit, which is equal to 1.6 times 10 to the negative 27th kilograms, plus a couple sig figs there, is approximately 931 mega electron volts. This is not actually a whole lot of energy if you think about it. Let's talk about 931 electron volts, or mega electron volts, not being a whole lot of energy. I've waved my hands at this number, and we should really take a moment to talk about it. In a day, the average American takes in 2,000 food calories, or 2 million regular calories, because a food calorie is 2,000 calories. At 4.184 joules per calorie, that means we take in 9.368 million joules per day. We've previously established that an electron volt is an electron's worth of joules, or 1.6 times 10 to the negative 19th joules. And a mega electron volt then is simply a million electron volts, or 1.6 times 10 to the negative 13 joules. One atomic mass unit is 1.66 times 10 to the negative 27th kilograms. If we apply Einstein's E equals mc squared, then 1.66 times 10 to the negative 27th kilograms times 3 times 10 to the 8th meters per second, the speed of light, but squared, is almost 1.5 times 10 to the negative 10th joules, times 10 to the negative 10th. These are very tiny numbers. 1.49 times 10 to the negative 10th joules, converted into mega electron volts, is 933 mega electron volts. Not the 931 that we saw in the presentation. However, I also multiplied by 3 times 10 to the 8th meters per second, not the exact speed of light, which is 2.99 times 10 to the 8th meters per second. Let's talk about two of the larger nuclear reactions that we know occur. Fission. Fission is the splitting of one large nucleus into two smaller nuclei. It occurs when the nucleus is bombarded with a single particle or a small particle that causes the nucleus to deform, as mentioned previously. When that nucleus deforms, the two parts of the nuclei are able to get far enough apart that their electromagnetic repulsion then rips them apart. The result of this on a small scale is some radiation and some heat. However, on a large scale, it actually gives off enough energy to destroy a city. The first nuclear reaction was observed by Otto Hahn and Fritz Strassmann and Lise Meitner in Germany. They were trying to make a new element, and what occurred when they fired a neutron at the nucleus was it actually split and became krypton and barium and gave off a lot of heat. It was not what they expected, but slowly they realized that this was actually a repeatable thing, and it started to be called a fission reaction. What makes a neutron a good bullet? Think about it for a moment. A proton is a bad bullet. Why? Because it's positive, and a positive particle is going to repel from a positive nucleus and never make contact, which is what we saw in Rutherford's gold foil experiment. An electron would attract to the nucleus, but it's still a bad bullet to fire into the nucleus because it's really tiny. That would be like me shooting ants at you, and that would be annoying, but ultimately it wouldn't really do anything. But a neutron is reasonably massive and neutral, so it's not easily deflected. And so a neutron is actually what is used as the bullet that breaks apart the nucleus of a large atom. One of the most common fission reactions that we discuss is the fission of uranium-235. Uranium-235 is an unstable nucleus, and when it decays, it gives off krypton, barium, 3 neutrons, 2.5 neutrons actually, if we're being honest. What does that mean, 2.5 neutrons? That means for every 100 fissions, 250 neutrons will be given off. And it also gives off 200 mega electron volts. Remember me saying 931 mega electron volts was not a whole lot of energy? This is about a fifth of that, so it's even less energy. So if it's even less energy, why is it a big deal? Well, imagine if you were doing that fission reaction hundreds and hundreds, maybe even thousands of times. How much energy could we get then? That is an interesting question worth answering. So let's take a look at uranium-235. The molar mass of uranium-235 is 235 grams per mole, or 0.235 kilograms per mole. For those of you who do not know what a mole is basically a package of molecules or atoms. The same way we would talk about a ream of paper, which is actually 500 sheets of paper, we can talk about a mole of atoms, which is 6.022 times 10 to the 23rd atoms. So 1 kilogram of uranium-235 is actually 1,000 moles, or 6.022 times 10 to the 26 molecules or atoms that will fission. At 200 mega electron volts per fission, that's 12.044 times 10 to the 28th mega electron volts. Or for those of you who are really dedicated to scientific notation, 1.2044 times 10 to the 29th mega electron volts. That works out to 1.927 times 10 to the 16th joules. That's over 2 billion days of eating on a 2,000 calorie food calorie diet. So while one fission does not release a tremendous amount of energy, a lot of fissions release a ridiculously devastating amount of energy. In this example, we use just 1 kilogram. Turns out that you get enough energy that it's actually worth building a nuclear power plant around it. We can actually produce enough energy from the splitting of the nucleus to run entire cities. Limerick Nuclear Generating Station, pictured here, is actually what generates the energy for most of New York City. So what exactly is going on inside of a nuclear reactor? Well, inside of a nuclear reactor, you have uranium fuel rods, which makes sense that you would have some kind of fissionable material as the fuel rods. You also have something called control rods inside that reactor, and we'll explain what control rods are for in a moment. But through fission, a source of heavy water, or deuterium-rich water, is heated beyond its boiling point. How do we heat it beyond its boiling point? We keep it under pressure. So there's a pressurizer, something there for people to gauge what's going on inside there so that the pressure doesn't become too high. This hot circuit of water is then actually used to heat a separate radiation-free regular source of water to boiling. This source of water is heated to boiling. That steam is then used to turn a turbine, and that turbine turns a generator, which ultimately generates electricity to power a city. So again, we have uranium fuel rods or plutonium fuel rods that are using fission to heat up a source of deuterium-rich water beyond its boiling point because it's kept under pressure. This super hot water source is then piped through but does not make contact with another source of water. This secondary circuit of water is heated to boiling, and that steam is then used to turn a turbine, which generates electricity. Depending upon the design of the nuclear power plant, some nuclear power plants will vent the majority of this steam into the environment. Other nuclear power plants will instead put this circuit of water across a condenser and recool the water to go through the process again. Why is it important to keep these two circuits of water separate? Well, the last thing you want to do is vent radioactive water into the environment. So these two sources are kept separate. So what's the deal with control rods? What is that about? Well, I mentioned that every uranium fission releases, on average, 2.5 neutrons. We round that to 3 for the equation. If it's giving off 3 neutrons, then those 3 neutrons are colliding with 3 more uranium and then giving off 9 neutrons to collide with 9 uraniums, which will give off 27 neutrons to collide with 27 uraniums, then 81, then 243 neutrons. This is exponential, no? This is a rapidly growing reaction. Control rods are there to absorb those neutrons out of the reaction so that instead of it being 1 to 3 to 9 to 27 to 81 to 243, instead the reaction goes 1 to 1 to 1 to 1. Literally, control rods keep the reaction under control. Good neutron absorbing materials are materials like cadmium or boron. Those are what are typically used to make a control rod. What happens if we don't use a control rod? Well, if we have a small sample of uranium, all of the excess neutrons are able to escape and release their energy in a reasonably fast fashion, and you just get a lot of heat and radiation. But if the sample of uranium is at what we call critical mass, then those neutrons cannot escape, and instead we have those collisions and that energy building and building and building on itself until finally it reaches the ends of the sample and releases a devastating amount of heat and wind and radiation. Critical mass is the minimum mass required to create a self-sustaining, uncontrollable chain reaction. In the case of uranium, it's approximately a kilogram. The mass of uranium that was used in the bomb that was dropped on Hiroshima was 2.2 pounds of uranium, or 1 kilogram. In the 1930s, people started discovering fission reactions. In fact, Fermi and some others were doing fission reactions under the bleachers at a university because they needed someplace out in the open to do it. It wasn't long before people realized that this was something that could be usable. And in fact, the German government began to realize that this could be usable. And by the German government, I mean the Nazi regime began to realize that this could be useful. So in 1939, Albert Einstein took it upon himself to write to Franklin Delano Roosevelt regarding these developments in Germany. It reads, "Sir, some recent work by Enrico Fermi and Leonard Szilard, which has been communicated to me in manuscript, leads me to expect the element uranium may be turned into a new and important source of energy in the immediate future. Certain aspects of the situation which has arisen seem to call for watchfulness and, if necessary, quick action on the part of the administration. I believe, therefore, that it is my duty to bring to your attention the following facts and recommendations. In the course of the last 4 months, it has been made probable, through the work of Joliot in France as well as Fermi and Szilard in America, that it may become possible to set up a nuclear chain reaction in a large mass of uranium by which vast amounts of power and large quantities of new radium-like elements would be generated. Now it appears almost certain that this could be achieved in the immediate future. This new phenomenon would also lead to the construction of bombs, and it is conceivable, though much less certain, that extremely powerful bombs of a new type may thus be constructed. A single bomb of this type carried by boat and exploded in a port might very well destroy the whole port together with some of the surrounding territory. However, such bombs might very well prove to be too heavy for transportation by air. The United States has only very poor ores of uranium in moderate quantities. There is some good ore in Canada and the former Czechoslovakia, while the most important source of uranium is Belgian Congo. In view of this situation, you may think it desirable to have some permanent contact maintained between the administration and the group of physicists working on chain reactions in America. One possible way of achieving this might be for you to entrust with this task a person who has your confidence and who could perhaps serve in an unofficial capacity. His task might comprise of the following: to approach government departments, keep them informed of the further development, and put forward recommendations for government action, giving regular attention to the problem of securing a supply of uranium ore for the United States. To speed up the experimental work, which is at present being carried on within the limits of budgets of university laboratories, by providing funds, if such funds be required, through his contacts with private persons who are willing to make contributions for this cause, and perhaps also by obtaining the cooperation of industrial laboratories which have the necessary equipment. I understand that Germany has actually stopped the sale of uranium from Czechoslovakian mines, which she has taken over. That she should have taken such an early action might perhaps be understood on the ground that the son of the German Undersecretary of State, von Weizsäcker, is attached to the Kaiser Wilhelm Institute in Berlin, where some of the American work on uranium is now being repeated. Yours very truly, Albert Einstein. This started what became known as the Manhattan Project. It was called the Manhattan Project because it was initially located in New York City, in Manhattan. Quickly, everybody realized that maybe they shouldn't be doing an experiment like this in a well-populated area. So it eventually got moved to the Los Alamos Laboratory in Alamogordo, New Mexico, on White Sands Missile Range. So the Trinity site is one of the few places that I've been to that Bill has not. And in fact, I've been there twice with my children and my father. And so I'm going to take you quickly through a little slideshow of some of the things that you can see when you're there. So some of the other things that you can see there are actually what's left of the tower that they raised the gadget or the Trinity test bomb up into. And that's what this image is here. You'll also be able to see a large, huge, heavy metal cylinder. Initially, when they were planning on testing a plutonium bomb, which is what the gadget ultimately was, they were going to use a large metal cylinder to drop the bomb in so that they could collect up the excess plutonium in casks. So uranium was a difficult refining process because you were taking uranium-235 and separating it from uranium-238, and it's, you know, about a 1% difference in mass that you're trying to separate. But plutonium was even more difficult to get a hold of, and so they really wanted to, because plutonium's a man-made element, so they wanted to be able to collect the plutonium up in case the gadget turned out to be a dud. Ultimately, they didn't use it because they realized that if they dropped the gadget and it detonated at all, it would more than likely completely disintegrate this large metal cylinder that they had made. And for size reference, you can see my dad standing there. He's about 5'9" inside that big metal cylinder. There's also a model there of the bombs, the Fat Boy bomb and the Little Man bomb. You can go visit the McDonald Ranch House, which they have painted and tried to preserve all of the original things that scientists had written, like please use other doors, keep this room clean, and please wipe feet, no shoes. You know, they haven't changed it much beyond keeping the paint looking the way it did back then. You can see some homes that are in disrepair. You can see the pool, the cooling pool that they used, that the folks working on the atomic bomb actually swam in that pool on the weekends. That was for if they had reactions that went out of control that they needed rapid cooling for. They had a pool of water on hand, but it actually became a recreational pool for the scientists and their families on the weekends. Security there was supposed to be excellent, but Richard Feynman used to sneak out from under a hole in the fence and walk around and come in through security, and security would go, "What are you doing out here? You're not supposed to be out here." And he would go, "Well, I left," you know, like I clearly left. And they would go through all the security clearances to let him back in. And then he would sneak back out under a hole in the fence and come back in through the front gate again, infuriating security. The obelisk has a little tribute written there that it's the location of the detonation of the first atomic bomb. And, you know, that is pretty much what's left there today. This is a picture from the first atomic bomb detonation. This was the tower that the bomb was raised up onto. And the second photo there is showing you the obelisk that resides there now. It turns out that upon the detonation of the test bomb, that tower was pretty much completely destroyed. So they've put an obelisk in its place. This is an aerial view of the Trinity site at the time of detonation. You can see the blast radius and the crater that was left there. Also, if you go to the Trinity site, they'll have all kinds of photos up for you to look at that show the scientists actually working on moving equipment into what was called the McDonald Ranch House, where they actually assembled the bomb. They needed to have a completely clean space to assemble this bomb, and so they actually put signs up on the door that said things like, please use other room. This is a clean room, you know, like take your shoes off at the door. Please wipe feet. Because in a place that was covered with sand, they had to put together a clean room. Other things that you'll be able to see if you go to visit the Trinity site include models of the two bombs. So let's take a moment to talk about the bombs. The bomb that was dropped on Hiroshima was a uranium trigger, which meant that we were reasonably confident that it was going to work because it was simply firing a uranium bullet into a uranium target. The plutonium bomb, however, was a bit more complicated. So the Hiroshima bomb was called Little Boy because it was small in size. It was dropped on Hiroshima on August 6, 1945, and it was about the equivalent of a 15,000-ton bomb or a 15-kiloton bomb. And the pictures that you see there are models of what Hiroshima looked like from aerial photographs before and after. Again, these are models rebuilt from photographs. These are not actual photographs, but you can see the total desolation, the devastation that occurred with the dropping of this bomb. Nagasaki got a plutonium bomb. Once we were confident that we would be able to create a plutonium bomb and that it would detonate, that was what was sent to Nagasaki. A plutonium trigger actually uses an implosion trigger. So it's a series of, it almost looks like a metal soccer ball, and it's a series of electrodes that at the time of detonation, electricity is used to go into these metal plates and push everything together and compress it. And that's actually what triggers a plutonium bomb. But if you have one plate not go off at the same time, it doesn't detonate. So that was the fear with the plutonium bomb. So Fat Man, which was a significantly larger bomb, was dropped on August 9th, 1945. It was a 20-kiloton bomb. And here you can see actual aerial photographs of what Nagasaki looked like before and after the dropping of the bomb. And again, the markers on there are just simply for size and to reference you for where ground zero is. But if you look carefully, you can see this large object, whatever this is, building, stadium, mass, whatever it is right here, and you can see what's left of it over here. Okay, so these were huge, devastating bombs. But they were both fission bombs. There's also another nuclear reaction called fusion. Fusion, unlike fission, is the merging of two smaller nuclei into a larger nucleus. This is what actually heats the Earth from the outside. Fission, because we have a uranium core on the Earth, is actually what heats the Earth from inside, but stars heat the Earth from the outside using fusion. We already discussed binding energy, and we know that when we take individual nuclear masses and we bind them together, it actually loses mass. In a fusion reaction, when we bind nuclei together, that mass defect, that loss of mass from the nucleus, actually emerges as energy. A tiny amount of energy, 17.6 mega electron volts. Remember, an atomic mass unit is 931 mega electron volts. But if you're doing this many, many, many millions of times, that 17.6 mega electron volts per fusion really starts to add up. I like to think of it as the Grand Canyon was made by a trickle of water, but given enough time, there's enough water to make the Grand Canyon. We have enough nuclei fusing in a star that it's actually quite impressive. So a hydrogen bomb or a fusion bomb is kind of like a turducken of bombs. In order to detonate a hydrogen bomb, you need to make it as hot as the sun if you can. Well, what do we know of that can get as hot as the sun? A fission bomb. A fission bomb can get as hot as the sun. So what we do to ignite a fusion reaction is we detonate a uranium bomb. But what do we do to detonate a uranium bomb? We use TNT to fire a uranium bullet into a uranium target. So it's a turducken of bombs. A TNT bomb with a fission bomb to detonate a fusion bomb. So happy Thanksgiving, but for bombs. Fusion, because of the abundance of hydrogen that's in the environment, produces an enormous amount of energy. But because we're trying to fuse positive nuclei together, it actually takes a tremendous amount of energy to get it going, right? So what's happening in space is gravity is becoming so great that as these particles come close together, they can't help but to avoid each other, or they can't help but to collide with each other and begin the fusion process. So it only happens at hot temperatures, like as hot as the stars. In order for us to do that on Earth, we need magnetic chambers to hold the material in place. We need lasers so that we can carry particles into the reaction. It takes an awful lot of energy to get fusion going. And you guys might be a little young for this, but if you remember the Tobey Maguire Spider-Man movies, Dr. Octopus was obsessed with creating a self-sustaining fusion reaction. They actually did a really good job of kind of depicting a sun, a little tiny sun that he had created, you know, the power of the sun in the palm of my hand. They actually did a really good job depicting that. So today we've talked about a variety of things relating to the nucleus of the atom. We've talked about the 3 types of radioactive particles, 2 of which are ionizing radiation. Remember that radiation in moderation is not the end of the world. Ionizing radiation is capable of damaging your cells and causing things like cancer, but we aren't dealing with the deleterious effects of radiation until we're reaching higher levels. People give off radiation, food gives off radiation, rocks give off radiation. It is when we're dealing with radiation in excess that we have problems. 2 other major nuclear reactions that we talked about are fission and fusion, both of which on an individual level do not produce a whole lot of energy, but we also do not typically deal with fission or fusion one atom at a time, but rather hundreds or thousands of atoms at a time, which actually produces a tremendous amount of energy. And while there are lots of differing opinions on whether or not the United States should have ever used the atomic bomb, I would argue that the development of the atomic bomb actually led to a wide variety of medical treatments and discoveries about the atom that would not exist today had we not been in pursuit of the ability to create that bomb. So, oh my gosh, I'm boring myself to death. Okay. That was a dumb thing to record. Okay. Okay. So, that's all wonderful to know. Yay, fun. But, so now let's talk about these 3 forms of ionizing radiation. Now, why did I erase that diagram? I don't like this. Then a uranium might turn into a thorium. If it's giving off beta radiation, then we might see it turn into something else. And I have to look at my periodic table to know. That difference in mass gets turned, oh Jesus. Nuclei become,